you'll be happy to know that after this chapter, I figured out how to break this up into more pieces parts. In the first part of chapter 11, we talked about liquids and how to identify intermolecular forces. Well, in this part of the chapter, it's a little more definitional, and we spend more time looking at things that are affected by intermolecular forces and definitional stuff. Okay? So the first thing we're going to talk about is, getting this right, is cohesion and adhesion forces. Okay, cohesion are intermolecular forces between similar molecules. Okay, and this is where they're similar, so they want to stick together. Adhesion, on the other hand, is intermolecular forces between differing types. And we'll talk about how you see this in lab. When you see things in lab, you'll see problems. Okay, so, and cohesion is molecules sticking together. Adhesion that are similar types. Adhesion are different types. And usually you're thinking about really opposite things like water and glass. Okay? For adhesion. Okay, one of my favorites is surface tension. And surface tension has an interesting definition. It's the amount of work that needed to increase the surface area. So it's the amount of work needed to increase the surface area. Surface area. So, if you think about it, when you see drops of water, and they do a slow time situation of it, then you'll see it pulling down like tear shape, and that's the raindrop portion. And then once it's free of where it's coming from, it balls up. Because what it's trying to do is minimize the surface area. And basically what it is it's the force of attraction between particles of a liquid. And so these are actually fun things that you can do. A liquid that cause surface tension. So this is actually a cool experiment that you can do. Everybody has isopropyl alcohol of some percentage in their kitchen cabinet, but if you put it on wax paper, you put a drop of isopropyl alcohol and a drop of water, drop of oil, you'll notice that they spread out totally differently. It has to do with the fact that and so what it's trying to do is minimize the surface area if it has strong intermolecular forces. So water does this. So for example, I like this little water strider. And the water strider works by its leg. You've got to blow up here. Its leg is really, really narrow and broad. So what it does is it distributes the weight. And as long as it doesn't break the surface tension of the water, then you don't have a problem. And it can walk along the water. Now, there are any variety of ways to mess up the surface tension of the water. One of the best ones is just adding soap. And you can see that it messes up surface tension really well. Okay, so that's one of the properties that is seen. Another one is viscosity, which is the resistance to flow of a liquid, and actually technically is the measurement or the measure of the resistance to flow. And the unit for it is called poise, which I just find that funny, so that's why. You're not responsible for knowing that the unit of viscosity for me is poise. But if you'll notice over here, we've got the SAE 40 and the SAE 10. What is that? This is motor oil, okay? So the 40 tells you it has higher viscosity and the 10 is lower viscosity. So you want higher viscosity in the summer and you want lower viscosity in the winter. And so if you'll notice on this chart here, as you increase the number of carbons, because decane has 10, 9, 8, 7, and 6, then your viscosity increases. So as you increase size of the chains, you tend to increase viscosity. And this is why syrup and stuff is very viscous. Okay? The next one is capillary action. This is the attraction. I lost my R. Attract. No, I can't spell. Attraction between a liquid and the walls of the container. Now, this is most interesting and has been used most often in glass. So if you look at it over here, they're drawing a drop of blood. They do this a lot of times if you're having your iron tested, they prick your finger and then they put this little piece of glass that has two pieces together and they put it up there and it's like your blood just sucks in, but there's no mechanical force doing it. It's just the attraction. And here you can see that you've got glass walled containers, those tiny tubes. And if you'll notice that the wider the gap is, the shorter it is, the more narrow, the farther up it is. They tilted this one showing you that it'll go up at an angle. And this is actually how water gets to the top of trees. Is capillary action is once it gets to the top and one evaporates off, it's kind of like pulling tissues out of the box. It pulls the next one up. But this doesn't work if the liquid inside is not attracted to the outside walls. Capillary action occurs when there is an attraction. If there's not an attraction, you get nothing. So, for example, if you were to do the same thing with plastic tubes, like that were larger, some plastics it would be attracted to, some plastics it wouldn't be. But like straws, they don't move up. Like these rubber straws we have now that are soft, there's no capillary action. You can't see through it. But if you've got a see-through plastic straw, there tends to be no movement up. If you have a glass straw, you can see that it is moving up. So, fun things to play with. Okay? We're back to the movement. The meniscus is the interface between a liquid and the air above it. And the walls of the container. But in some cases, we are concave. We call this a meniscus. Remember when we were in lab? Meniscus. We talked about reading from the bottom of the meniscus. Okay. Now, on the other hand, and you'll see this with the water, this is concave. The water is going to rise up because it's attracted to the walls of the container and the air is not a problem. On the other hand, this one is convex. This is mercury. Mercury does not want to interact with either the walls of the glass container or the air around it. It wants to interact with itself, so the net effect is it's pulling in together, and as it pulls in together, it pushes up because of the lack of interaction between it and the walls of the container. Okay? Now, another thing that comes into play is the enthalpy of vaporization, and this is the energy needed to change a set amount of liquid to a gas, aka a vapor. So it's vaporization. And you remember seeing a curve similar to this, is that this is the lower temperature in blue, the higher temperature. It doesn't matter how low the temperature is, you're always going to have a few molecules with enough energy to evaporate, but at higher temperatures you have a much greater number that have the minimum energy to kinetic energy to escape. This is why if you take and hang a towel that's wet on the line outside in the summer, it dries very quickly. In the winter, it's still going to dry. It just takes it a whole lot longer because you need a lot more energy to accomplish the same. Okay? Dynamic equilibrium, remember, is where the rate of the forward reaction or process is equal to the rate of the reverse reaction. So what we're basically saying here is that things occur at the same rate. So what happens here is once you've reached equilibrium, you're evaporating at the same rate as you're condensing. So the net effect is that the number of particles in each state remains constant. Particles in each state is constant. Now, this can be reactions, this can be processes, this can be a variety of things. Okay? So what we're doing here is the vapor pressure in a closed container. And if you'll notice, when we first make the setup, it's not at dynamic equilibrium. It has to make it to that point. Okay, and how does it do that? Well, vapor pressure is the pressure of the gaseous molecules above the liquid. Above a liquid. Okay? So if you think about it, vapor pressure is just how much of the liquid particles have moved to the gas state. Now, volatile is often used interchangeably with flammable, and it's not the same at all. Volatile means that the easy, well, there are a couple ways to define volatile. That volatile means is it's going to vaporize easily. Vaporize easily. That means there is low attraction amongst the particles. Traction among the particles. So anything that has low intermolecular forces has low attraction and therefore will be volatile. And gasoline, when you're pumping gas in summer, we're coming up on summer, and it's really warm outside, you can see the vapors escape the gas tank as you're pumping. that means that the gasoline is a volatile substance. Now, gasoline also happens to be flammable. However, carbon tetrachloride is very volatile. It's 1 carbon and 4 chlorides, because the only thing it's got going for it is London forces. But carbon tetrachloride doesn't want to burn. So it is volatile but not flammable. So one of my pet peeves is when people use them interchangeably. Okay? So, so a low vapor pressure would be a non-volatile substance. And this is actually, we're going to use this phrase later, but basically non-volatile means that it's not going to vaporize at all. Things like, okay, sugar tend to be non-volatile because, yeah, leave them in the pantry, they're still there ages from now. Okay? Now, boiling point is the temperature at which the vapor pressure of a liquid equals the atmospheric pressure above it. Okay? So, and again, this is usually a dynamic equilibrium, so the rate of the forward process equals the rate of the reverse. Now, let's go back and talk about the boiling point, because the boiling point, if we define it, and it is defined as when the vapor pressure of a liquid equals the vapor pressure above it. When we talk about being in New Orleans is below sea level. So that means the atmospheric pressure is higher in New Orleans than it is in, let's say, Denver, Colorado, which is known as the Mile High City. If you approach Denver, you're like, wait, it's flat. The mountains are actually behind Denver. When you approach it, it's very, very flat. And you're like, what do you mean it's the Mile High City? I thought we climbed. Well, you are climbing. You have climbed since you left New Orleans. New Orleans is below sea level. Denver is a mile above sea level. Well, what's that mean? So the atmospheric pressure above Denver is much, much less than that of New Orleans. So if you're ever cooking brownies or anything else, and you look at the package, oftentimes it will have high altitude instructions. And because the atmospheric pressure is lower, the boiling point is lower. Therefore, in order to get the food cooked, you either have to increase the temperature or increase the time you cook it at a given temperature because your boiling point is lower. So this is the net effect of how boiling point is affected by atmospheric pressure. That's also why pots with a lid will boil faster, because you're doing an artificial increase. Okay, so where does that show me and tell me? Well, these are boiling points. This is the atmospheric pressure. And what we're looking at over here is the temperature versus the vapor pressure. And the definition of boiling point is when the vapor pressure of the liquid equals the vapor pressure of the atmosphere. So if you'll notice, diethyl ether, which is CH3CH2, OCH2CH3, not that you have to know this. This has London forces and dipole. Ethyl alcohol is CH2,3CH2OH. This one has London forces, dipole, and a hydrogen bond. Whereas water has London forces, dipole, and 2 hydrogen bonds. So it has the most. And then ethylene glycol is CH2CH2OH. OH. So if you look at it, it has a whole lot more of everything because it's got more size, more polar bonds, and more hydrogen bonding. So if you'll notice down here, we're not even on the chart. Another name for ethylene glycol is antifreeze. And it is a sugar. Ethylene glycol has been banned. I think they're using propylene glycol now as antifreeze in your car. I can't remember what it is, but antifreeze is toxic to animals because it tastes good. But so if you'll notice that as you increase the intermolecular forces, you increase the boiling point. So boiling point, remember we said, had a huge effect on the intermolecular forces. Okay? That brings us to our phase changes. Now, in our phase changes, this shows energy up here. Yet a lot of people think of temperature. Temperature is only one form of energy. So on this diagram, we're going to use energy here. What we're looking at is the phase changes. This is solids. This is liquids. And this is the gas forms. So if we move from a solid into a gas directly without going through a liquid, we call this sublimation. If, on the other hand, we go from the gas down to the solid, we call this condensation. No, we don't. It's getting late, guys. So this is called deposition. I knew when I wrote that was wrong. Okay, so we've got sublimation, we've got deposition, moving from solid to gas or gas to solid. Going from a solid to a liquid, we call that melting. Okay, going from a liquid to a gas, we call that vaporization. All right, obviously spelling is optional for me. Vaporization or evaporation. Going from a gas to a liquid is condensation. And going from a liquid to a solid is freezing or fusion. Now, the reason why we have two terms here is some of them have become more common and colloquial. Other ones were used. So when we talk about ice formation or ice melting, we're going to talk about the heat of fusion, and as opposed to anything else. Now, you want to know these transitions based upon what you have here, because you may very well encounter multiple choice questions. All right, that brings us to the heating curve of water, and FYI, in the next chapters I have broken them up into smaller parts, which is really good for you and for me. I tend to not lose my mind so much, and you tend to be able to go back and look at things. I'm not sure what I was doing when I did this, but anyway, bear with me. Okay, so this is called a heating curve, and what it actually has in it is it has actually a variety of information in it. This is the amount of energy added. This is the temperature. And what you'll notice is we're going to start down here. And if this happens to be water, we're dealing with ice. So as long as we're just all ice, we can raise the temperature of the ice, but we do not change the state. So we can actually have ice at different temperatures. And you know this because you can have liquid at different temperatures, so you can have ice at different temperatures. Now, once you hit 0 degrees C, you level off in temperature because you're using all your energy to convert from a solid to a liquid, or if you're going the other way, from a liquid to a solid. If you're going this direction, energy is added. If you're coming back, energy is given off. So if you'll remember, this is endothermic, and this is exothermic. Whoops. Okay, so much for my spelling here. All right, once we have reached the point where we have got all of our solid melted and all we've got is a liquid, then we start rising again. We continue putting our energy into the temperature of the liquid until we hit 100 degrees C. If you have liquid water, it cannot be a higher temperature than 100 degrees. So once you keep adding energy, then what happens is it starts converting the liquid to the gas. Once all of the liquid has vaporized, then it continues rising temperature. Okay, so this is ice changing temperature, water changing temperature, and steam changing temperature. This transfer of the salt to liquid or liquid to solid to liquid or liquid to solid is the freezing point. The boiling point is when we move from the liquid to the solid or the solid to the liquid. And if you may have heard of boiling water in a Dixie cup, this is what happens if you boil water. You can boil it in a cup as long as the cup does not touch the flames. As long as there is water in the cup cannot burn. If you put the flames on directly, yeah, all bets are off. But if you've got it above it, you can keep raising the temperature. As long as you've got water in the cup, it will maintain the temperature. This is why if you have a choice between a steam burn and a boiling water burn, take the boiling water burn. Don't take either one. But if you've got to avoid steam, steam can go up 200, 300, 400 degrees real quickly. It creates major issues with respect to burns, because your body is mostly water, and so you vaporize things. But it's a much higher temperature, so steam burns are way worse than water burns. Now, how do we make these transitions? Well, if you remember back in chapter 5, it's calorimetry, and we did the specific heat capacity of water. But the same thing works for moving through ice and steam. Notice it takes more energy to move water up in temperature than it does for ice or steam. This is why ice melts quicker and steam picks up temperature and burns better. The variation here for moving from solid to liquid or liquid to solid is the enthalpy of fusion and vaporization. It takes more energy to vaporize than it does to change it there. But notice that these units are joules per gram per K, and these are just kilojoules per mole. So here we need the moles, and here we need the grams and the temperature change. And remember, it doesn't matter whether your temperature is in degrees C or Kelvin, because the difference will be the same. We're going to look at setting up a problem here. And on this problem, I'm going to set it up, but I'm not really concerned with you being able to work it. I'm mostly being concerned about you being able to set it up. So remember, if we start at ice and go to steam, we're putting energy in. If we go from steam to ice, we're giving energy off, so it's negative. Okay, so the question here is how much energy is transferred when 225 grams of water is converted from steam to ice. Okay, so we're going to start at steam. For the steam, we're going to move it from 165 degrees C to 100 degrees C. So for steam, that is a Q problem. Delta T is equal to 65. Okay, so it's a Q problem, and remember Q is equal to grams times the enthalpy, or the specific heat, times delta T. So this would be 225 grams times the specific heat of ice, which is 2.01 joules per gram, okay, times 65, okay. All right, to move from steam to water, then that is still a Q problem, but the Q is equal to the heat of fusion, heat of vaporization, fusion is melting, times the number of moles. So if we were to go back up here and convert 225 grams to moles, 0.016 grams per 1 mole, that gives us a whopping 12.5 moles. So that is going to be the heat of 0.7 kilojoules times 12.5 moles. And one other problem is either we need to be all in joules or all in kilojoules. So just out of meanness, 1 kilojoule is equal to 1,000 joules. So we can multiply that by 1,000. Then from there, we're going to go from water at 100 degrees to 0 degrees. So delta T would be equal to 100. So the Q is equal to the mass again, which is 225 grams, times the specific heat of water, which is 4.18 joules per gram per K, times 100. Okay. And then we're going to change liquid water to ice. So again, that would be the Q, which is the heat of fusion, times the number of moles, which I'm starting to run out of room, so I'll put that together. So that's 6.02 kilojoules per mole times the 12.5 moles times 1,000 joules per 1 kilojoules. And then we're going to move ice from 0 degrees C to negative 8 degrees C, which means my delta T is equal to 8. So Q is equal to 225 grams times the heat of fusion of ice, which is 2.09 joules per gram per K, times delta T, which is 8. So if we're going from steam to ice, then once we total the energy and then give it a negative sign because we're giving it off. If we were going the opposite direction, we would add it together. And out of sheer entertainment value, if you want to work these, I got 707,458.25 joules if you want to work it. I'm more interested in you knowing the pieces, parts of the curve and what's going on at each step than the overall. Okay. So that brings us to the Clapeyron equation, which involves looking at temperature versus the natural log of the slope of vapor pressures. And you can look at that little lanyap. This brings us to phase diagrams. Phase diagrams are an interesting 3D way to tell you a whole lot of information. There's a saying that says a picture's worth 1,000 words. And that is very true. So in a phase diagram, you have pressure increasing over here and temperature increasing over here. And we can see all three phases with a variety of things going on. Now this figure has all the information you need in it, but it's kind of hard to see. And I didn't define, it's going to relate the physical states of a species to temperature and pressure. Okay, so as I said, this one's a little bit busy, so here we're going to keep it simple. We have solid, liquids, and gases. If you sit on this point here, then you're talking about, in this case, the deposition sublimation state where you're going back and forth, but you have both phases. Okay, here's the liquid, here's the gas, here's the critical point. This is the point at which gas and liquid is indistinguishable. I have a cool slide, indistinguishable. It might be an IBL. I told you I'm a bad speller. Anyway, you can't tell the difference between the liquid and the gas, and we call that a supercritical fluid. This point here is the triple point. This is the only point where all three phases exist at once. Unlike the lines where these are going back and forth between the two, but if it's sitting on the line, it's sitting on both phases. Okay, and phase diagrams show a lot of information in a very short period of time. They're a variety for different ones. Notice this is for water, and this is water, and this is CO2. Notice that even though they've got the pressure and the temperature the same, the scales are different. And if you'll notice, the curvature, here's like the critical point here is much lower than the critical point up here. And it varies for species to species, but you always have a triple point, and you always have a critical point, and you always have the solid, liquid, and gases. And notice over here you have a huge amount of gas. Here you have a huge amount of gas. And your liquid area is larger. So it'll vary from species to species. To me, these are fun and simple and easy to use. So, for example, if we're working a problem here, what are the physical state of the molecules at point G? Well, the first thing we have to do is look at it. And I like to go ahead and write it in. This is solid, this is liquid, and this is gas. So if I'm at point G, I am a liquid and a gas. Okay, I have both states going on. And then what are the temperature and pressure at point F? So if I take this down, and it's really good to use a straight edge if at all possible, but it's fine. The temperature is about 0 degrees C, and the pressure is about 0.5 atmospheres. Okay, and point E is the critical point. If I had asked you what point D was, that would have been the triple point. So these are simple questions and often asked of species on a phase diagram. So you want to make sure you can read this. Here's a conversion from, this is the previous Pearson text we used, but I love this picture because you can see here where you have the gas and the liquid states, and then they slowly start moving until you hit this point where you're increasing the temperature, and the pressure is also increasing because you're in a closed container, and you can actually see where you have a supercritical fluid. So this is actually really cool to see. And critical fluids, especially of carbon dioxide, are becoming more and more useful in terms of separating species. For example, caffeine removal from coffee. Now, as far as I'm concerned, there's no point in drinking coffee if you're going to take the caffeine out. But there are worlds of people who drink it without it. So one thing is they used to use benzene, which is a known carcinogen. You can get it out, but you always leave a little of whatever. Well, what they found is they can use supercritical fluid that of CO2, which will separate it easily. And then the beauty of it is once you take the pressure off or you increase the temperature, guess what? The CO2 evaporates. So it's an easy use to separate things out. All right, properties of water. Now, this to me is a really interesting, you don't have to fill in this thing. I just want you to think about it. Most solids expand when they melt. Water condenses. So if you put ice in a cup, it's going to occupy more room than it does if it was liquid water. And this is really important because when ice freezes, it gets less dense. So it freezes on top. Think about a lake where you have a whole lot of fish. Think about what would happen instead of the ice floating as if it went to the bottom. Everything would be squished. We would not have fish overwintering anywhere that there's ice. So this is an interesting feature that goes in here. It has the largest surface tension of any common liquid except mercury, which is critical, not the mercury part, but the liquid part, because you're mostly water. And so if it wasn't for water having high surface tension, you'd be a big puddle. It's an excellent solvent. It dissolves just about everything. It has a high specific heat, which is very critical because, again, you're made mostly of water. And your body can only handle so much temperature-wise. So if it didn't take a lot of energy to raise the temperature of water, you would pretty much combust when you got a cold or something else because you would have too high of a temperature. And compared to other species or members of its family, the melting point and the boiling point are much higher, which again is critical because of the concept of you being a puddle. Okay, so reread these and think about them with respect to the human body. All right, liquid crystals is the section 11.7. I'm going to not cover chapter 12 and this section of 11, but I'm going to have you work on I want you to read over it. I just don't want to take the time. So what I'm going to have you do is submit a paper answering some of the questions associated with these species. I want it typed, etc. That'll be posted. I'm going to try to post it when I post the lectures so that you can go ahead and be working on it. It needs to come in before the exam. When is the exam? The exam will be posted as part of the syllabus. So make sure you look at those and pay attention to what it says. And we are done with this chapter. I apologize because I did not split this chapter up and into as many sections as I should have. I do better with the next chapters. So this chapter is only 2 big segments. Yes, they're huge and I do apologize. But you can go through and read them. The next one I have broken up into more, and just you can pay attention to it and fast forward through the parts you don't want to review again.